Hey, hello everyone. This is week 5, and we are talking about integration by parts. And in this video, we're going to talk about a specific type of integration by parts. So we will talk about some type of integration by parts integrals that they have some sort of invisible one. So let's see some examples. So for the first example is integral of ln of x dx, and as you know, we don't have any easy formula for this. You didn't, like, when you learned the antiderivative on that table of formulas, that was not the antiderivative of ln of x was not included. And if you think about other techniques of integration that you learned, for example, substitution, it's impossible to use substitution to solve it. So you just learned the technique which is called integration by parts. So you'll see that this integral will be very easy using integration by parts. But you might think, in order to apply integration by parts, we need to have multiplication of two functions, and here there is only one function, which is ln of x. The answer here is we have an invisible one, actually, so we can consider that this is ln of x multiplied by 1 dx. So now, in order to apply integration by parts, we need some part of this multiplication to be u and some part to be dv. The general rule is that you always take dv, the part which is very easy to find its integral. So, and the part which is very easy to find its integral is 1, because if you take dv to be ln of x, it's still, we don't know how to find its integral. So u is the other function. So I let u to be ln of x, and then I find du, which is going to be dx over x, and then I let v, or dv, not v, to be dx, and or 1 multiplied by dx. I just not write 1 because it's not doesn't affect anything. So then I take v is the antiderivative of dv, which is the antiderivative of dx, and that's x. Okay, so now I'm just back to the integration by parts formula, which is uv minus the integral of v du. And uv is going to be x, and x is v, u is ln of x, minus integral of v du. So now v is x, du is dx over x. And if you simplify this x with this x, you will get x ln of x minus integral of dx, and that's x ln of x minus integral of dx is just x, because antiderivative of, you can think about it, antiderivative of 1, and that's just x. And don't forget plus c. If you find the derivative of this function, you'll see that we are back to our original function ln of x, and this means that we find the integral, the answer of the integral correctly. Okay. So now I have a question. What about x ln of x? If we have multiplication of some other function by ln of x, then maybe integration by parts is a good technique to apply, which is here, because x and ln of x are two different type of functions. And what we're going to do here, we are not going to use that invisible one method. Why? Because here it's much better to, and if you use the invisible one method, you will see that you're not going to end up with any answer. You can try it and see. It will make the integral more complicated. So here, the way that we're going to deal with this integral, you let u to be ln of x, and you let dv to be x dx, and then you continue with this. I'm not going to answer this question because I just want to talk about invisible one, but just to give you an idea that what is the difference between this integral and when we have like integral of ln of x dx only. So here you have multiplication of another function, and that's why you're using that other function to be dv. But here, because there is no other function, we consider that invisible one to group it with dx, and then we'll have dv for 1 multiplied by dx. So next example is integral of tangent inverse of x dx. So a group of integrals that we are using that in invisible one technique for them are the trig inverse function. So we always use the trig when you have only a trig inverse function in an integral and it's not multiplied by any other function, you always use the integration by part and that invisible one technique. So here you are letting u to be tan inverse of x, and it means du is dx over 1 plus x squared, and then you let dv to be dx, or 1 multiplied by dx, the one which is here and it's invisible. So I'm not going to write it. It equals dx, and this means v equals the antiderivative of dv, which is the antiderivative of dx, and that's equal x. And now you apply the formula for integration by parts. That's going to be uv minus the integral of v du. And if you want to remember this v du, because sometimes students confuse it, is this v du or u dv? Just remember that v is the new function that we get, du is the new component that we get. So you multiply the new things basically in this integral. So now you have uv, so you have x tangent inverse of x minus integral of v, which is x, multiplied by du, which is dx over 1 plus x squared. So now x tangent inverse of x, we don't have any problem with it, but we have another integral, which is integral of x. So if I want to rewrite this in a nicer way, so it's x tangent inverse of x minus integral of x dx divided by 1 plus x squared. So now we need to figure out this integral of x dx over 1 plus x squared, which is very easy to figure out. This time we're going to use substitution method. Why? Because if you let 1 plus x squared to be some letter, for example t, I'm going to write it here. So you let t to be 1 plus x squared, and then you will get dt equals 2x dx. So divide both sides by 2 to generate that x dx in terms of t. So we divide by 2, dt over 2 equals x dx, and it means that we have that x tangent inverse of x minus integral of dt over 2 divided by 1 plus x squared was t. So now this is equals to x tangent inverse of x minus, so now you can bring 1/2 outside of the integral and you will have dt over t, which you know its integral is by the formula dt over t. Integral dt over t is ln of absolute value of t. So minus ln of absolute value of t plus c. Don't forget to rewrite everything in terms of x. So now we have x tangent inverse of x minus ln of absolute value of, which we don't need the absolute value because 1 plus x squared is always positive, plus constant c. And that's the final answer of this integral. So here I have an example, which is an exercise, not an example. The antiderivative of sine inverse of x dx. I have the final answer. I included the final answer for you, so you can check your answer. But remember, you will follow exactly the same pattern like the antiderivative of tangent inverse of x dx. And whenever you have a trig inverse function, and it's alone in the integral, there is no other function is multiplied by it, you always use that invisible one technique for it. Okay, that's it. Have a very nice day, and I'll see you in another week video. Bye.